maximum principle, right? So what's the proof, right? Anybody want to start? All right. Yeah, I know it's Friday. Okay. All right. So let's just go through it. Okay. So let's take the maximum, okay, on the boundary to start with, right? So that we don't have to just keep writing that. Okay. And let's let V, as AJ was saying, is just going to be equal to U with epsilon x squared, okay? And as you might expect with epsilons, we're eventually going to take that quite small. So if we flip around the, if we rewrite our PDE, but now that operator acting on V, and shift everything to the left-hand side, then the t derivative, right, of this just has u in it. The x second derivative now has this additional term that's going to help us push things slightly below 0, okay? And essentially, since u of t is equal to a xt uxx, then that vanishes, okay? And that means that, yeah, this is just equal to minus 2 epsilon, which is going to be less than 0, okay? So now we set up our contradiction, right? So we know that this has to be strictly less than 0. Let's create a situation where we have a interior max such that it's such that we violate this condition, okay? So if we suppose that V has a local max on U sub t, and it'll be at some point that we'll just label as x0, t0, with t0 less than t, okay? Then what do we know about that? Well, what do we know about local maxes? We know 3 things, at least.
Derivative is 0 at the point.
Yeah.
So derivative 0, so the t derivative 0, the x derivative 0.
And Laplacian is less than 0. Less than 0. Yeah.
Oh, vxx? It's less, yeah, it's less than or equal to 0, right? So you could have the second derivative be 0, right? Like think of a quartic function or something like that at 0, right? So we can only say it's less than or equal to 0. So that's why we have to deal with this construction, right? So this implies that v sub t minus a xt, v sub xx, right? So this is 0, and then this thing is greater than or equal to 0. And then this thing is actually strictly greater than 0. So the whole thing is greater than or equal to 0 at the point, okay? But what's the problem here? Well, remember, we have this, right? But if we go back to this slide, we see that, well, it should be strictly less than 0, okay? So this is a contradiction. Our previous result, okay? So this implies what? V cannot have an interior maximum, okay? And in particular, sorry, let me back up here. Local max on UT here, okay? But I'm going to say this only holds for t less than capital T, right? So I sort of skipped over that part, right? So if you think about this, right? If this is t equals capital T, this is t equals 0 here. This is what, x equals 0 and x equals 1, right? A maximum point here, right? You have to have your derivatives be 0, right? But up here, right, you could have a maximum where u sub t is actually greater than 0, okay? So you have to be careful with this point. So we deal with that point separately, right? So this shows that it can have an interior max basically on ut for t less than t, okay? And then if we take on t equals t specifically, right? Assume v has a max, a local max, right? At some point x1 t, okay? So what do we do with this? We sort of follow the procedure of the previous part, but v sub x, right? That's 0. V sub xx, that's going to be less than or equal to 0. But now v sub t is greater than or equal to 0, okay? At x1 t, right? And this again implies that v sub t minus a x t vxx greater than or equal to 0, okay? Again, this is a contradiction, okay? So it's not a big deal, right? I mean, you could technically write this up here and then you could handle all these cases together, but it's just good bookkeeping to separate them out, okay? So therefore, okay, and I think this, is this where we need continuity? By continuity, right, the max of V on our boundary, or sorry, our closure, right, of our domain occurs on gamma t, right? Because it can't occur anywhere on the interior, so it must occur on the parabolic boundary, okay? Furthermore, this implies that u xt plus epsilon x squared, we can bound this from above, right, by the max of yt over our boundary of uyt plus epsilon y squared, right? So wherever that boundary happens to be. And this means that this is bounded from above by max on the boundary of u plus, right? This thing can't be bigger than 1, right? Because x ranges between 0 and 1. So let's just call that epsilon for now, okay? And this is true for any xt that lives in the closure of ut, okay? So now we've just written out our max bounding, right? And now we have something that we can manipulate that involves just u of x, basically on the closure, right? So we're almost there. We just need to shift some things around. So what I need to do now, right, is to just take this and move it over to the other side, and then I can get some additional bound, right? So let's do that. So the last step then is u of xt is bounded from above by, now the thing we called at the beginning our max, right? This capital M plus epsilon 1 minus x squared, okay? And I can write this as m plus just epsilon, right? Because the smallest that could be is 0, right? And now, since epsilon's greater than 0 is arbitrary, okay, we can basically have u xt less than or equal to m for any xt in the closure of u sub t, right? So the interesting thing here, right, is that we actually got a strong maximum principle for v, okay, because we had a strict enforcement that the upper basically the upper bound on v had to exclusively be on the boundary, right? But that only got converted into this weak maximum principle for u, okay? Here, what we're doing is essentially like taking a limit as epsilon goes to 0. We can sort of make this as small as possible, okay? And so that's how we sort of rid ourselves of this epsilon in this case. And yeah, so it's not clear to me that you necessarily need twice continuous twice continuous differentiability. Yeah, but I would say just to be safe, I would stick with that construction. Are there questions about this? It's not a lot different from, the one that we did in class. So when you're thinking about, things that could come up on an exam or, or the prelim, right? Think about ways that you could change the problem and see if you can still prove a maximum principle or not. How flexible essentially are the assumptions of a particular theorem, and what do you get basically if you don't have all the assumptions there. The other thing you'll probably see in some prelim problems, right, is sort of like using the maximum principle to prove um, uh, inequalities basically between solutions to different PDEs. So I think there's an example in the 2019 exam. So weak maximum principle, what can we do with the weak maximum principle other than create bounds for functions?
Uniqueness.
Yeah. So it's another way of proving uniqueness. That's actually, probably quicker than constructing an energy function argument, right? So, yeah, if you're sort of tasked with proving uniqueness and you've already proved the maximum principle, it's usually, much quicker just to jump to the uniqueness proof using the max principle. So let's just review that for interest here, right? If we go back to the original equation, right, and I say, essentially I need to prove that let's say u sub t equals a of xt u sub xx, and then let's take some boundary conditions here. You could make them arbitrary, right? And then if I have some initial condition, and I say prove this has a unique solution, right? Okay. then you can do it a few ways, right? But if you jump to this sort of construction saying that U1 and U2 solve the IBVP, right? Then essentially WT solves this. And then you can say that by the Max principle, right? W is strictly less than or equal to 0, okay, for xt in the interior. And also then by the min principle, W is greater than or equal to 0, okay, on xt is in here, okay. So this implies that W is explicitly equal to 0 and U1 is equal to U2, okay. All right, so takes a lot less breath than I think constructing the energy function argument, okay. All right, I think we're at time for today. Any other questions about the exam or